Okay. Again, thank you very much for the privilege to present DAOS to you all. I'm a member of the ALCF operations team. I work on the storage team within operations, and I've been working on DAOS now for about 5 years, standing up clusters for the last couple. Whoops, how do I advance? Here we go. This is NDA-free discussion. We won't be talking about anything that is NDA. All of DAOS is open source and able to be discussed. I'll start with an overview of Aurora, DAOS within Aurora, the hardware mostly, and then I'll branch into a DAOS architecture discussion. So you may have seen this slide before. This is kind of a high-level overview of the Aurora system. It's going to come in at just over an exaflop of performance. We know it's 10,000 nodes. And the bottom here on the high performance storage is our key for today's discussion. Any questions on Aurora in general? Okay, the Aurora, we've got 3 main file systems, actually 4. There's not one on this list. Kaushik's also going to go into these. The Aurora DAOS is our main high performance file system or storage system on Aurora. You can see that it's sized approximately twice the size of Eagle or Flare, our 2 Lustre file systems. The design of the size of the Aurora DAOS file system, it was designed to be large enough to hold an entire campaign's worth of storage without having to force that campaign to move data out of DAOS in order to process over the life of their project. Whether or not we've been successful at sizing it large enough will be seen, but that was the intention of creating it this large. You can see on the right-hand side, the performance is expected to be significantly higher, and I'll go into some of the reasons why that we're going to be seeing that high-level performance on DAOS. On the right-hand side, I've got a little cartoon of a node, and I'll go into that on a future slide. And the network architecture is quite interesting here. So what we've got on the left-hand side in the first 3 boxes are a cartoon that represents the compute nodes. The question mark, I should have substituted that for 166 compute nodes, compute groups. And then in these 2 center boxes, they represent 8 distinct IO groups for DAOS. You can also see that this purple line that represents the amount of network connectivity between the DAOS servers is significantly greater than any other network connectivity in the system. This is to allow the DAOS servers themselves to perform rebuilding and communications within the cluster and without impacting or stealing any bandwidth from the user side. Does that make sense? Any questions on the network architecture at a high level? So now we're getting into the meat of the node. And what we've got here is we've got in the lower right, we have what we call group 0. And in this group, we have user access nodes, the Lustre gateway nodes, system service nodes, including the leaders for HPCM and that class of node. All the DAOS nodes are shown here in the red. One of the notable things of DAOS versus the Lustre file systems is that DAOS is directly on the Slingshot network. In order to access the Lustre file systems, the traffic has to go from the compute nodes over these yellow gateway nodes onto the outboard Lustre file systems that sit on the ALCF InfiniBand network. So going back to the comment about the performance, that's one of the aspects of performance, is that the DAOS servers are directly on the Slingshot fabric with the compute nodes. There's 1,024 DAOS servers. I'll go into details on a future slide on the individual configurations. Any questions on this slide? Again, it's just positioning where the DAOS servers are amongst all the hardware on Aurora. Individual DAOS node details. This is an individual DAOS server. This is a 2-socket server. It's got 32 gigabytes of DDR4 memory. It's got 16 512 gigabyte persistent memory DIMMs. We're going to call this persistent memory, and we're also going to be referring to this as storage class memory in future slides. The key takeaway is that this is memory that is persistent. If you write data into this memory and power the node off, that data persists. The performance of persistent memory is slightly slower than DRAM, but faster than the latency associated with NVMe, which is a statement on its own, because we know that NVMe is significantly faster than going to a hard drive. There's 1,024 DAOS servers in total on Aurora. Each of these, as noted above, is a dual socket server, and each of these will run 2 DAOS engines. And I'm going to be going into this in more detail in the architecture presentation. Any questions on an individual slide here? The key is that there's 2 sockets. There's memory, Optane, and NVMe that are all on dedicated PCIe lanes that are dedicated to each of the 2 sockets. In other words, each socket has 16 gigabytes of DDR4, has 8 512 Optane DIMMs and 8 15 terabyte SSDs that are owned exclusively by that socket. Any communication that may be required between the 2 DAOS engines on a server does not take place within memory on that DAOS engine. It goes across the network. We've eliminated any cross traffic on a DAOS server over the QPI link between processors. Okay, so in reality, what we've really got is we've got a single node, a single hardware node that's supporting 2 DAOS engines that more or less think that they're independent from each other. Okay, and that's now I'll just update some of the performance. We have had a chance to run IO 500 on this cluster. The last results we've shown were for SC23 last year. I won't go into all the detail here, but we were number 3, and we're still number 3 on the IO 500 list. I'm now going to get out of the introductory and go into what is DAOS, because so far we've talked about this 4-letter acronym and we haven't added much detail to it. So the acronym itself stands for the Distributed Asynchronous Object Store. If we break that down, the distributed word is probably fairly obvious in the sense that there's 1,000 DAOS servers and that the object store is distributed across the 1,000 servers. The DAOS software ties them together and allows them to operate as a single cluster, as a single storage system. The asynchronous nature is got to do with the actual object store itself. And I've got a slide coming up that speaks to the VOS, or the versioned object store. And the object store itself is simply an object store. So this is different than block storage, like in a Lustre file system or in a GPFS file system, where the objects here, the objects here are objects. Sorry, that's kind of a redundant, but the objects being written are objects as opposed to a block. This DAOS was designed from the ground up to take advantage of NVMe. There's a lot of technology, a lot of features that help to differentiate DAOS from traditional PFS file systems. One of the keys is that it was architected from the ground up to support NVMe. It operates completely end-to-end in user space, which means that in most conditions, we can completely bypass any kernel calls. So from IO submission on the compute node to IO complete being issued back to that IO injection is all happening in user space. And it offers a shift away from the IO model for based on block device, and the high latency storage that's inherent to hard disk based file systems. The latency here is significantly lower. Design objectives of the overall DAOS design, I've only taken a few of them and I put them into this slide, the ones that I thought were the most interesting to speak about. High throughput and high IOPS at arbitrary alignment and sizes of IO. This is an important criteria. If we think about all of the optimizations we've had to do with block storage over the years, a lot of that had to do with alignment of IO. Am I writing on the proper 4K page boundary? That class of concern. DAOS eliminates those concerns. The advanced data placement algorithm that takes into account fault domains. So this is a programmatic placement algorithm. Where objects get placed is derived by running an algorithm. That doesn't need to go look for free space. It doesn't need to update an indirect block or an inode as blocks are allocated. It all happens via an algorithmically run placement algorithm. End-to-end data integrity. We'll see as we start talking about pools and containers that we have a high degree of flexibility with DAOS in order to pick almost exactly a container or an access model on top of DAOS that suits our application workloads. We can pick from redundancy versus erasure coding. We can pick to choose none of those and to run the risk of having a node go down. We can choose that we want to do end-to-end data integrity. We can choose that we only want to check the data integrity as data is read back to a client after being written to the server, or we can choose to have the data checked as it's being written on the server and again after it's been read from the server and just before it's been given to the application buffer. So we have a lot of flexibility into where we want to do end-to-end checksumming here. And obviously there's a cost associated, but given the flexible nature, we get to choose where we're going to pay that cost. There's a security framework to allow access to the pools that I haven't described yet. In a lot of ways, the pools that I will be describing are analogous to a Lustre or a GPFS project space or a project directory. It's a private area where your team, your project will store and write its data. It will not be necessarily accessible by any other team, but you do have control via ACLs to allow access for other teams, other groups at varying levels of access. There's a software design management layer to provision, configure, modify, and basically do all the DAOS. And this is basically the DAOS product and the DMG, which is the management interface into the DAOS product. And there's a seamless integration that I'll speak a little bit in a future slide with the Lustre parallel file system. I would recommend anyone, I'm not going to be able to give justice in a short period of time to the overall architecture of DAOS. However, there's an excellent write-up at an Intel site, and I would recommend people who have more questions or, in fact, a curiosity about how we do this work to fully explore that. Any questions on this slide? So what are the features? How do we achieve some of this? So DAOS relies on OFI, the Open Fabric Interface, for low latency communications and stores data on both the storage class memory, the PMEM, the persistent memory we spoke about a second ago, and NVMe storage. DAOS itself, the object store itself, presents a native key array value storage interface. On top of that key value interface, there are what's called a container. It's basically a domain-specific data model that lays on top of the key value interface that allows you to utilize the key value interface through this container interface. An example of that, and one that we'll be talking about, is the POSIX layer. Okay, a POSIX compliant container that allows that container to look exactly like a POSIX file system, and we'll see that coming up. Now, the VAS, I referred to this a second ago, the versioning object store is the key technology here. The versioning object store is responsible for providing and maintaining the actual persistent object store for DAOS, for all the pools, for all the containers, for all the data in DAOS. The DAOS IO operations are logged and inserted into a persistent index. Each IO is tagged with a timestamp called an epoch. We then just absorb that IO. We don't need to worry about whether or not that IO has overlapped with an earlier IO. We simply need to absorb it and log it. Later in the cycle, and I won't get into all this level of detail in this presentation, unfortunately, but as the VAS IOs are executed, there's threads underneath in DAOS in the engines that are reconciling all the various IOs and writing those permanently. So it's able to absorb IOs very quickly, and there's threads underneath that are then doing reconciliation back into the pools, back into the containers. This link goes directly to the source code or the GitLab repo for the VAS, and there's an excellent write-up on the function of the VAS in this particular link I'd recommend. So we've talked about a lot of different things. How do we put all this together? What's a DAOS system? So a DAOS system consists of a set of storage nodes that are on the same network. So in our case on Aurora, these are all on the Slingshot network. The set has varied over our experience so far on Aurora. We started with a 20 node cluster that we exposed to users. We grew that to 24 nodes. We've now grown that to 128 nodes. These are all running within the 1,024 nodes. And at the same time that the ALCF is running their object stores or their DAOS systems, Intel is busy testing their own object stores on exactly on different nodes, non-intersecting DAOS server nodes within the 1,024, but we are running multiple object stores over the 1,024 nodes simultaneously. It's a really strong example of software-defined storage. So a DAOS system is some arbitrary set of storage nodes. The DAOS server nodes, and we talked about, are being dual socket. Each of the nodes runs 2 DAOS instances per node. We talked about that again. We talked about the affinity of a socket to its own PCI lanes, owning its own DC, its own PMEM, and its own NVMe. Membership of the DAOS servers is recorded into a system map. Each of the servers is given a rank ID. You'll often hear us talk about DAOS servers, DAOS engines, and ranks. These terms are almost synonymous. An engine subprocess. So now we're talking about the engine running on one socket with its own storage resources. That engine exports those storage resources to all the nodes in the network, including the compute nodes. And then within a DAOS engine, the storage is statically partitioned. This is getting a little bit deeper into detail. The topic I wanted to introduce here is the concept of a target. Whoops. And so there's some similarity here for people who are skilled in the Lustre area. We talk about OSTs and MDTs as being object system and metadata targets respectively. Here we talk about targets in a similar capacity. We don't necessarily break down whether it's SCM target or an NVMe target, but we do speak about targets per server, targets per engine. And again, I've got a link here and it goes into much more detail on the targets. But in a high level, you can think about a target as being analogous to an MDT or an OST. Any questions there? Hopefully I haven't glazed everyone's eyes over and lost you. Now, the final concept here is the concept of a pool. We've talked about the individual nodes. We talked about the amalgamation of those nodes or some arbitrary set of nodes into a server cluster. Then what we would do is we allocate a pool over top of all of those NVMe and SCM targets that are now exposed by all the engines. When we allocate a pool might be data science, it might be some particular project. But we tell DAOS we want this pool to be a certain size, and we can restrict it to only a subset of the targets in the system, or we can in fact have that pool exploit all targets in the system. So far at the ALCF, we've had all pools using all targets. That'll likely be the case. It's the case on the 128 node cluster, and it will likely be the case on the 800 node cluster we stand up for acceptance. There is some discussion that we'll eventually stand up user pools at 80% of the available targets. This would allow us to then grow a user pool. I don't want to get into all the details, but there's a bit of a challenge in the sense that a DAOS pool, when it's allocated, is a hard allocation. It's not a soft allocation like a Lustre quota, where you can simply change the quota and continue to grow. If we allocate a DAOS pool and then exhaust it completely, we're going to be forced to allocate a fresh DAOS pool of a larger size. Let's see, what have I forgotten on this slide? Targets, a pool identified by a unique UUID. We usually don't use UUIDs, but in fact, we use a label, which makes it human readable. But under the covers, it's important to realize that there is a UUID. The pool map, again, maps our active targets into the pool. If there is any sort of a target failure or an engine failure or a node failure, those targets will be excluded from the pool as though they're no longer available. The pool itself will automatically rebuild all objects within the pool that were or had data on those now missing targets. And again, there's an overview in the architecture. So here's a cartoon to kind of describe a little bit of what we've talked about so far. On the bottom of this cartoon, we have the DAOS server instances, and ... There's many of these DAOS engines. The DAOS engines themselves contain storage class memory and NVMe. There's administration, there's a control plane that administrators like myself use to control the actual cluster. Within the engine itself, we talk about the data plane, and that's simply for the ability for all the engines to speak to each other. On the top side of these red arrows is the user-facing client side of DAOS. Some of these blue boxes, I talked earlier about DAOS presents a native key value interface and then allows domain-specific containers to be used to access the KV. These are an example of the domain-specific containers. POSIX, which we'll talk about a lot, HDF5, MPIIO, and various other containers. There's interfaces through a native array, a native key value interface, and all the communications that's going on between the DAOS instances, the DAOS engines, and the clients is all over RDMA, again, in user space. What we're showing down on the bottom right here is going to be that we're eventually going to be building out other capabilities that are in conjunction with DAOS. For example, I'll talk about Lustre, namespace cooperation. HSM could be a possibility through Lustre, different kinds of capacity tierings. Let's see, what time is it? Am I missing? Oh, I'm almost out of time. Okay. This is a slide that kind of shows that there is, in fact, a POSIX and a DFS API for most of all of the calls. I'm not going to go into detail here, But seeing how we're focused on POSIX, I thought I'd do a comparison between things like makedir and DFS makedir. You don't need to worry about this unless you're writing native KV applications. Defuse is the DAOS fuse agent. A defuse is a way to mount an existing container, which we haven't described yet, which is kind of a problem. Let me carry on and we'll describe containers in a sec. When you execute a command like this, what you're saying is I want to mount from my pool, my container on this particular mount point. When that command executes in user space, you then can change directories and access your POSIX container as a native POSIX file system. If you CD into mount defuse, you'll be able to do ls, cats, dirs, VIs, everything you can always do to any POSIX file system. And that's really what this bullet speaks to. You now have a parallel file system under your mount point. Now, the interception library is a technology we haven't spoken to yet, but this works in conjunction with defuse, and it intercepts IO and it takes any IO calls that are destined for the defuse and issues DAOS IOs for all of the mappable IO calls in the interception library. What this basically allows us to do is to use a very minimum of any sort of POSIX IO early in the open process of a file. And from that point forward, all of the IO to that file takes place over DAOS itself natively using the interception library. Unified namespace is a convenience item. So far, without the unified namespace, you'd be forced to refer to all DAOS pools and the containers within the pools by their labels or by the UUIDs. With the DAOS namespace, there's going to be a file in a Lustre file system that you have created indirectly by the DAOS container create command. And by giving that container create command a specific option of a path name, that path name will be created in the Lustre file system. That path name will actually be a directory, and that directory will have extended attributes. The extended attributes will have the UUIDs of the pool and the container in DAOS, such that you can use that file as a substitution for those two pieces of data in most of the DAOS processes. I don't have an example, and I'm sorry about that, but watch our user-facing documentation for updates on the unified namespace with Lustre.
Gordon, in the interest of time, how many more slides do you have?
About 3 or 4, and I can accelerate through them right now.
Sounds good.
Okay, this model, this picture is only to describe that we have lots of options in DAOS. For example, on the left-hand side, we created redundancy groups, okay, using replication. In the middle, we've created redundancy using erasure coding. Erasure coding, for people who may not understand that term, RAID 5 and RAID 6 are both variants of erasure coding. DAOS is going to allow us to pick various different kinds of erasure coding and apply those to a container. And again, lots of options. I'm not trying to tell you what the options are, but simply that we have a lot of them. And again, going back to the concept of software-defined storage, we have lots of ways to approach user access to data. I won't belabor this. Paul and Kaushik talk about this a little bit. One of the key things is that you're allowed to create containers and data sets in DAOS that have absolutely no redundancy. They go very quickly. However, if any node or any rank or any target gets excluded, that file will have a hole in it. That the data that resides on that target that's now missing will no longer be accessible until that target's brought back online again. The recommendation is to create containers with some level of redundancy. Okay. And these slides are mostly all repeated in future presentations. I'm going to quickly accelerate. Not much to talk about here that's not talked about in the future. The key is that we have a QSub directive that's new for DAOS. We have a module support for DAOS on compute and UAN nodes. In order to request a pool, we require a little bit of information from you prior to pool creation. And then I can skip these. These are simply examples of a pool query and a container create command. There are links here. There's a lot of detail on container create on the DAOS wiki. And here's an example of container create, an example of mounting a container and doing a simple VI of a file, and then unmounting that same container. And with that, I'd like to thank you very much for your time.
Thank you, Gordon. And I do want to mention to the audience that we will provide all the slides to everyone. Kaushik?
Yeah. So hello everyone. Can you see my screen?
Yes.
So yeah, I'll be covering most of the things which Gordon covered, but in the perspective of a science application user, how will it be when he is moving his job from like say scripts from Lustre world to a DAOS world? I just want to quickly mention that Gordon mentioned Argon is at rank number 3. That was under the research category, which considers only the one node performance. But in production scale, production list, Argon is in number 1 for the IO 500 under DAOS category. It's just one node. Just want to show that one. And DAOS is Distributed Asynchronous Object Store. And in Aurora, we have only few ways to do I/O. You either use your DRAM, which is the /temp. There is a squash of us mounted there, and you have 1 terabyte of DRAM. You can store your files there. And the other file system is Flare, which has a capacity of 91 petabytes and 160 OSTs. So the maximum bandwidth you can get out of Flare is like less than a terabyte per second. And it should be noted that DAOS is a primary major file system on Aurora, and this is the most recommended way, especially with 230 petabytes of storage, and it is expected to deliver more than 30 terabytes per second. So there is also another Lustre store called Gecko, which is where your home directory is stored, and it's not recommended to run jobs from there. So basically, you are left with either using Lustre Flare or DAOS or just your TempFS. So Gordon covered most of the this part of the ecosystem from the hardware perspective, from the operations perspective. So I'll be covering the from an application user's perspective. So I just want to quickly make sure I covered most of it. So yes, DAOS is an object store. Your data is distributed across NVMe and SSDs, and most of the retrieval and storage happens asynchronous, and that's where your distributed asynchronous object store comes from. And all your objects are all your data is stored as objects, basically key value stores. And if there is some metadata access, all of the tiny data is stored on the DRAM. So your metadata is really fast for most of the Python related applications. Yeah, so we were able to get around 20 terabytes per second with just 300 out of the 1024 DAOS nodes. So these are real numbers, and we have DAOS running, and we have active users currently using DAOS. Feel free to ask me any questions if you have anything, but Yeah, I think it's answered. Okay, so here I just want to quickly show you the perspective of a node from in terms of the NIC. So if you see here, a compute node has 8 NICs, whereas a DAOS node has just 2 NICs. And each NIC is a Cassini NIC, and it's capable of delivering up to 25 gigabytes per second. So you can see that with 8 NICs on the compute node side, you can roughly get 200 gigabytes per node, and we have 10,624 compute nodes here. This is where your actual app is running. And all your IO on the DAOS will be stored on the storage node. So your process needs to read and write from here and go back here. So there are 1024 DAOS nodes, 2 NICs per node, and 40 gigs per second. So what this means is binding your ranks is very, very important for DAOS. So we have 104 cores, and if you want to use all the 8 NICs that I mentioned here, you need to bind the cores accordingly. So this is just a recommendation, not a hard and fast rule. I usually avoid the first row because the operating system is running. There are a lot of kernel stuffs going on. So I start from the second row. I just distribute and balance it on different regions of the CPU. Usually we have 12 GPUs, so most people would use 12 ranks. So I just distribute in this way so that all the NICs are almost equally efficiently used. And I use this CPU binding. So CPU binding is really, really important. And this is from one of our recent paper at PDSW. So here you can see that with the efficient binding, I mean with really hard coding all the cores that I want to bind and placing it more efficiently, you can see that around 4 process per NIC is actually needed to get peak bandwidth. Yeah. And this one is around, this one is about the injection. So, and each NIC should drive enough data to get the maximum potential from the NIC. So we found that it is around 512 kilobytes. So that is from the individual nodes NIC perspective. And if you look at the Dragonfly group, so this part is the compute group. So this is where your when you do a QSub, 8 nodes. So your nodes are your nodes are distributed here. I'm not sure if my yeah, your nodes are distributed here. And when you're doing IO to DAOS, it needs to talk to the DAOS nodes here. So whereas in Lustre, suppose assume your compute nodes are here and you're trying to do IO on Flare, which is our old Grand. It needs to go from the compute network all the way to the service group, and then it has to go through the gateway nodes, and then it has to enter the Grand file system. So there is a lot of bottleneck there, and if you compare it with DAOS, it's right on the compute network fabric, so it is very close. And you can see that these are assume you can these big boxes are individual cabinets, racks. So there are 166 cabinets or racks. I just want to quickly make sure. Yeah. So and it is in 166 Dragonfly compute groups, whereas the 1024 DAOS nodes are in 8 DAOS groups. So that means each DAOS groups have at least 64 racks, and you can see that each computer cabinet has a dedicated link to each of the DAOS groups. So for example, if you focus on this one DAOS group, you can see that all 166 cabinets have a direct link to the DAOS nodes. So why I'm talking about this thing is it is when you do a QSub, normally the nodes that you get are distributed across everywhere, and it is important to use all the if you really focus on performance, and if you want to squeeze out the best numbers out, then you need to place at least one compute node per rack so that you use this global highways, all the dedicated green links, 166 green links going to the DAOS groups would give you the best performance. Like, this is something you cannot control. Like, you can try with placing with the node placement and things like that, but in a rare circumstance, if you get all your 8 nodes placed on one cabinet, you might not see the 5 terabytes per second or 30 terabytes per second. It won't happen, but it's just a picture that it's good to see. And within the DAOS group here, we try to place the DAOS nodes as equally as possible, however different number of nodes we have currently running. So what is step 1? So when you come to DAOS, the first thing is you need to email support@alcf.anl.gov, send your project name, the usernames, and how much space you want, and justification, and you will be given a pool. So what is a DAOS pool? DAOS pool is a dedicated storage for your project. This is fully dedicated for your project. So unless you have a DAOS pool dedicated for your project, you can't start anything with DAOS. So this is kind of the step 1. And once you have a DAOS pool, then you can make sure you have access to it or not by DAOS pool query and your pool name. So more on this later, but you can quickly see how much space you got and the targets and is there any errors or something. This is just to make sure you have access to a DAOS pool. And these are some sanity tests. Like, often we get the question like, is DAOS up or down? And so the first thing we have to do is we have to use module load DAOS. So you need to use soft modules, and then you should load DAOS. And these are some sanity tests just to make sure if the module is loaded, is the DAOS client process is running. And clush is like a PDSH command, which takes this command and run it on all the nodes. If you want to do ls on 1024 nodes, you do clush hostname and do ls, and it'll run ls on 1024 nodes. So same thing. We just make sure DAOS is running or not, and then DAOS pool query. So this is just a simple sanity test if things are running or not. And when you do DAOS pool query and your pool name, you have to just make sure if there is any errors, it'll be shown here. If it is disabled or not, and most of the things is repeated before. And in case if there is an error like transport layer Mercury error or something, that means my DAOS is down. So you can send a mail to support, or we'll let you know by notifications. There is also one more an error message like out of group member list error. So those are just a lot of messages that's getting printed. That message will be fixed in the next version of DAOS, and that can be safely ignored. But if you see this one, something is wrong, you cannot proceed anything more. This is like the first steps here. So once you're done with the DAOS pool, the second thing is DAOS container. In a simple words, you can think DAOS container is like your sub project directory. That's it. Like you can assume like now you might go to /Lustre Flare projects hack or somewhere like so. Similarly, your pool name would be your project name, and your container name could be like a certain feature, and you can put all your files there. It's as simple as that. For a DAOS POSIX container, you can assume it as like a top level directory. You just create a directory. And we also have different types of containers like graph container and columnar container, HDFI container, which will be which are in experimental phase, and I'll cover those later. But once you have a DAOS pool, the next thing is you need a DAOS container. And how do you get a DAOS container? You just create one. DAOS container create, a POSIX container, the pool name that you got from the support, and you can put any label that you want, and you can set the redundancy factor. So the redundancy factor is, suppose if one of the DAOS servers goes down, you'll be able to build back your data from the other redundant servers. So there are a lot of intricacies that can be added here, like increasing the redundancy factor, like adding optimizations like O-class, file O-class, all this. Deep dive will be covered by Paul in the next talk. So, but this is the first step. So once you have the DAOS pool, you create a DAOS container, and then you can verify it by DAOS container list your pool name, and you will see the container listed here. So you will also see a UUID. This might be the unique number for your container. This might be useful for you later. I think similarly, you will also have a pool UUID. So here there is a pool UUID in the DAOS pool query here. So just to note, it will come later. So there are other tools like you can get the properties of your container, list the containers. So list the containers is this one, just listing what are all the containers in your project pool space. And in case if you want to test your container is everything is okay, you can do the DAOS container auto check and pool auto test and things like that. And if you want to delete a container, you just do DAOS container destroy. So just a quick overview on the model. So what I have covered till now is the pool, which is something ALCF allocates for your project. That's the bigger level directory, and container is something that you create, and all your data will be objects, which is basically a distribution key and attribute key. So there are different ways how your object is stored, but this is just a general high level view. And once you have your pool and container ready and tested everything works, so there are three modes that you can play with DAOS containers. One is the POSIX mode, the MPIO mode, and the DFS mode. So POSIX mode is just like a terminal, like there's really nothing complicated there. So for example, here I have my I have mounted a container in this location. You can see my pool name is data science. My container name is IO test. I did this by launch. I'll show you how to mount your container. It's basically you go to this directory in LS. This is your DAOS container space. Whatever you put here will be inside your container. That's it. This is a simplistic POSIX container. This libDFS is an emulation layer which collects all those objects and presents a POSIX view for us so that we are able to interact with the container. And the POSIX container is built on Fuse emulation layer. So it goes through the user space and then the kernel space and then goes to the libDAOS file system. So the DAOS Foundation has given us an interception library, which will bypass the user space and it'll give you a better performance. So I'll cover these things in the coming slides, but there are a couple of interception libraries called libIO IL and libPIL, which will improve the speed performance. So basically we have three modes. The POSIX mode is directly just throwing your files there and reading it from there. And there is MPIO mode and DFS mode. DFS mode is directly talking to the DAOS libDAOS library. And when you use this interception library on the POSIX mode, you will get very close performance to the libDAOS. That'll be really as fast as using the DFS mode. I'll cover those things later, but just that in a high level, you have three modes to interact with DAOS. So now that you have a DAOS pool and DAOS container, you can mount anywhere. You can mount it on a compute node. You can mount it on a login node. You don't need to wait on a queue sub. So if you are doing it on a login node, you just create a directory and use start diffuse, provide the directory, your pool name and container name, and that's it. So all these commands are not needed. This is just to prove that there is something mounted here, as I showed you. Once you do that start diffuse on the login node, and you'll see that this is the location where the DAOS container is mounted. And I think and then you can go to this location, temp, pool name, container name, and you'll see your data there. You can CP there, MV there, and you can do as you always do. So this is from the login node. if you are doing the if you are mounting the DAOS containers on the compute node, you would just use launch diffuse. So launch diffuse will automatically mount your container on temp, pool name, container name on all the compute nodes. Suppose you have 1024 compute nodes, it will be mounted there, and you can do the same things there. And when you're done, you can do the unmount by clean diffuse. Even if you don't do it, the PBS scheduler in the epilogue, when it comes out, it automatically unmounts it for you. So these are the two ways that you can mount a container anywhere. So the benefit is, suppose you have a large job running on 8,000 compute nodes for several hours. You don't need to spend another 1 hour copying your data back to Lustre or somewhere. You can just leave it there and then come back to a login node and mount it there, and your data will be there. So there are more details on how to move your data from DAOS and Lustre will be covered in the last few slides. So this is just about mounting. So till now, what I have covered is, for the first thing is you have to verify you have access to a DAOS pool, and then you create a DAOS container, and you can mount it on anywhere like your login node or compute node, and do all your CPMV, whatever you want to do in that space. And the next thing is using it on MPI exec. So as I mentioned before, so let me show you here. Yeah. So there are a couple of interception libraries that would give you very close performance as the native DFS mode. So that is libpal. So libpal, the difference between libpal, liboal is libpal also redirects the metadata and the data through this path, whereas liboal, only the real data goes to this path and metadata still goes to the fuse path. So basically, if you use libpal, it will be faster. So that's what I've added here in the LD preload, and the same thing as you always do. This is an example from Thunder SVM project. So you do MPI exec, the total number of ranks per node, you do the CPU binding, the one core per NIC thing that I mentioned. And if you are using DAOS, you need to add this --no VNI, and all these things are, even whether you use DAOS or whether you use Lustre, all these things remain the same. You might have a wrapper, you'll have a binary, and you'll have the arguments that passes to your application binary, and then you'll show a path where your actual data is present, or where you want to read from, where all the compute node wants to read from. You just change it from, instead of Lustre projects, Flyer Aurora deployment, you would just change it to temp pool name, container name here. 1 second. Can I create a new container using the existing container as a baseline? That is, I would like to have a new container with the data. Oh yeah. Yes, you can make a copy of containers and you can move data. There are tools available for that, which I will cover in the last few slides. Alex Mitten. So this is how if you are, this is how you do run a MPI exec with DAOS. So the only difference is the LD preload part. There's a no VNI, and you would change the path of where your data is actually stored. These are the only changes with and without DAOS. So as I mentioned before, there are different types of container. There is also an experimental container called Python container. So you can natively interact from a Python terminal to the Python container, but this is still in the experimental phase. So what is the difference between your Lustre JavaScript and DAOS JavaScript? So the only thing is you would add -l DAOS equal to default in your QSub. Previously, you did not have that. When you're using DAOS, you need to have that. So even here, when I have a, let's see if I can, so I have this job. So you can see that I used -l DAOS equal to ops, but this is a different cluster. You would be using -l DAOS equal to default. Only then you would be able to do the module load DAOS. So that might be a problem if you don't use the -l DAOS. So this is the one difference on the QSub. And you would do the module load DAOS and mount your container on all the compute nodes using launch diffuse. add your LD preload interception library, change your path. And even if you don't do this clean diffuse, the PBS epilogue would do it for you. So this is the change from your Lustre world to the DAOS world. Okay, does Globus work with DAOS? What's the best workflow to send terabyte? So I'll cover this one later when I cover the data mover part. So this is the difference from when you do a QSub as well as when you do a MPI exec. And as I mentioned before, there are 3 modes: POSIX mode, MPIO mode, DFS mode. I showed you the POSIX mode, which is basically this location, the pool name, and so this is how you do the POSIX mode. And in MPIO mode, the difference is you would add the DAOS ::, and there are optimizations that you can do, which Paul will cover on the MPIO mode. And the third part is the DFS mode. So if you note this DFS mode, which is something, it's very close to the native file system, and it'll be faster. So on the third mode, DFS mode can be achieved in multiple ways. The first one is if you use this libpil interception library on the POSIX container, you would eventually get as close performance as the native DFS. Or if you're going to do it on your program, this is a simple program which shows the DAOS APIs, like similar to MPI init. They have like a DFS init, DFS connect, your pool and container. You also have DFS open, DFS write, DFS read, DFS disconnect, and DAOS finalize. So I'm just showing at a very high level on how to talk to the native layers. There is also the different DAOS walls that the IO libraries might provide. I know there is a HDFI wall, ADS wall. They would also give the direct native performance by talking directly to the DFS layer. So interception library walls, this is the DFS APIs, and -8 DFS is I think I had -8 DFS is from the IOR. If you want to do some IO benchmarks, IOR supports -8 DFS. If you pass -8 DFS instead of -8 POSIX, it would do the IO benchmark directly on the DAOS. I have an example in the coming slides. So now that you know, you can interact with the DAOS containers in 3 different modes: POSIX mode, MPIO mode, and DFS mode. We also have an experimental darshan for DAOS from the MCS IO team, and we don't have a module load darshan for DAOS ready, but I think around December or Jan we'll have that. But if you want to try it immediately, it's very straightforward. Like you just load the module load, you do module load DAOS and clone the darshan repository, check out the DAOS branch, and run .prepare.sh, .configure, make install. And you can now also specify where the binaries would go in, where the logs will be saved, and so on and so forth. So just make install will install that darshan for DAOS here. And this is a one-time thing that you need to run this Perl script so that there are the structure like 2024, August, 2023, all those tree structure is created. And when you run this DAOS config log path, it will also show where the logs are getting stored. This is a quick install, local install for profiling DAOS for darshan. So here is the example with the -8 DFS. As I mentioned before, IOR, you just pass -8 DFS. It's directly talking to the DFS layer. And you need to add the lib darshan preload first, and then the libpil second. And it should be noted that darshan currently supports only the DFS level layers. And so that's it. Like you just add a preload in the front, and you will have your darshan .darshan files generated in the log directory here. So now once you have the .darshan file, you will ship it back to your laptop, and you need to have a darshan util. So the one that I previously showed is a darshan runtime tool, and this is a darshan util tool. So if you are coming from the Lustre world, you would have seen all these nice plots from darshan, which we don't have yet for darshan for DAOS, but I think Shane is currently working on it, and we'll have it in the future. But currently we can use the darshan parser tool and see the darshan profiler statistics for DAOS. So basically you just create a Conda environment, install SPAC, and SPAC install darshan and darshan util. If you are using it on Mac, this environment variable is needed, and then you just run your binary darshan parser and provide the .darshan file that you got when you ran this LD preload with darshan, and it will be stored in this location. So you just bring it back, and you can run it with parser, and it'll give you the statistics. So that's about darshan. And now on the data mover tools.
Kaushik, how many more slides do you have?
1, 2, 3, 4, 5.
Okay.
So now if you have a lot of data, suppose configuration files and the actual data that your app needs to use, or if you want to move it from Lustre space to DAOS space, you just create a POSIX container, mount it, and you just do a CP. That's it. CP from your Lustre space to your temp pool name container name. And the DAOS also gives a lot of custom tools called DAOS CP, DCP, DAOS copy. And there's also an rsync, dsync, and dtar. These are all under the MPI file utils bin under experimental category, but you can always use the DAOS file system copy to copy from a copy, like if you want to move a petabyte from one place to another place, you can use this. And there is also a question on the cloning a container. All those details are in this location. So I just want to quickly show you how it looks. So this is an example from Thunder SCM code. This is their job script. This side is the Lustre way. So basically they load their necessary modules, and they just run MPI exec. So in order to change it to the DAOS way, you just need to load module load DAOS. All these things are not necessary, I would say. This is just for a sanity check. You would create a container if you haven't created it before on a login node. Even this is not necessary, and you would mount it. And you would copy your the real sim data file that Thunder SCM is using from the Lustre space to the DAOS space. And if you have already done it on the login node, you can completely avoid it. And on the MPI exec, as I mentioned before, the LD preload is an addition, and you just mention the data where it is present on the DAOS temp pool name container name. So this is the difference if you want to change your application code from Lustre to DAOS. And I think I also have another example from Hack. The same thing. This is on the Lustre space. This is on the DAOS space. You can see that I have this -l DAOS in the queue sub default. I load the DAOS module. I create a container. I mount it, and then I just have the preload before. And then in the location where I read or write, I change it to the temp pool name container name of the file instead of the Lustre locations. And this is the only change when if you need to migrate from your Lustre world to DAOS world. And so we have a different number of DAOS nodes up most of the time, and we are getting currently we are running at 128 nodes. And I think by early November, we'll have 600. So when these are approximate bandwidth expected, and how we'll achieve there. This is just for reference. It's not hard and fast rule. Suppose if you have 128 DAOS nodes out of the 1024 DAOS nodes currently up and running, you will be, we expect at least 5 terabytes per second bandwidth. So this is an example from the Hack IO benchmark. So when they ran on Lustre, the Lustre's theoretical peak maximum is 600 gigabytes per second. We cannot get any more than 600, even when you use all of the OSTs and MDTs. So you can see that we got close to 600. And when we had around 20 DAOS nodes, we were able to get 900 gigabytes per second with just 2% of the total DAOS nodes up and running. So, and some best practices, when you feel something is not working, just make sure, did you use -l DAOS? Did you load the module? Did you query your pool? Do you have access to it? Was the DAOS client process running on all the nodes? Did you mount it? Were you able to do an LS on this location? If there's something really strange, you can do the DAOS container get property. So let me see if get property on my pool name, container name. You can see that it shows healthy, and make sure if it is unclean or broken or something like that. And you can also see the if your space is full or something. So here you can find that if it minimum shows like 0 KB, that means you have already used up all your space. That could be also the reason why DAOS is not working for you. And you can also do the DAOS pool auto test and DAOS container. It is good to check all these things before you reach out. And that's it from my side. So these are some of the references. Let me know if you have any questions. If I understand.
Thank you.
So basically, I'll be doing a little deeper dive into the user experience of how to optimally use DAOS, and then going over some of the internals of how the data movement works, and how we're going to be advising you to make certain settings on your containers. So first of all, there is an MPI driver for DAOS. It's implemented in the Intel MPI version that's installed of InPitch that's installed on Aurora. Basically, it uses the DFS API that Gordon and Kaushik touched on to do all the accessing to DAOS through. And the way that you use the driver, as Kaushik said, you could either append DAOS to the file name of your of the file that you're going to use, or you can set this environment variable Romeo FS type force equals DAOS, which will inherently make every single file access you have through MPIO go through the DAOS driver. And that's especially useful if you're using HDF5 and PNCDF with MPIO as a backend. You might not be able to set the file name explicitly, so you can use this force instead. And then there has been some work in Romeo or InPitch MPIO to auto detect DAOS, so you won't have to do this anymore, but that's not currently in our build on Aurora. So once that gets there, you will no longer have to do this, but until then you will. As Kaushik touched on, there's Darshan support for DAOS. Use Darshan parser. There are now DFS and DAOS modules with DFS files and DAOS objects, UUIDs that you can get information on. You can either build Darshan yourself with the spec install, as Kaushik mentioned, or I've got a pre-built one on Aurora that you can use basically with this LD preload command. Oops, sorry. With this LD preload command, as long as you're a member of the Aurora deployment project, it's built with HDF5 and PNCDF support, so the more you have to specify those shared libraries explicitly, and then then follow that with the pill for DFS IO intercept library that Kaushik touched upon. And the one caveat to doing this, if you're using MPI IO, is that if you use the Romeo FS type force option to tell MPI IO to write everything with the DAOS driver, Darshan's going to use that as well. So you have to put your Darshan log file in your fuse mount in order for Darshan to work. And this will eventually no longer need to be done once the Romeo InPitch auto detect is implemented. But until then, you'll have to explicitly set the Darshan log file to be in your diffuse container. And then once it's there, then you can just move it to Lustre and run Darshan parser on it. And this whole thing will eventually be incorporated in the modules, as Kaushik mentioned. And then also, if you want any help in analyzing your Darshan logs to understand performance bottlenecks, I'd be happy to help you with that. So this slide is an attempt to explain the data movement and data integrity of DAOS in the context of this erasure coding. So what this example is showing is us in a container of a POSIX type, a single shared POSIX file across with data inside of it across several nodes. And this is an example of the data just on one node, how this data is going to be chopped up and distributed across servers within DAOS. So when DAOS goes to store an object, it looks at the object in terms of bytes and byte offsets, and essentially, if our object type is if our container type is a POSIX container, then these byte offsets are going to be the same thing as the file offset in bytes. So what this is going to do is basically, when in the case of a write, DAOS is going to look at file domains in terms of the EC stripe width and the EC cell size. So the EC stripe width is basically the number of servers that we're going to use to store the data for one transaction, and then each server has a parity value of 2. So just to walk through this, it's going to take a look at the first megabyte of offset, and it's going to use 10 EC cells of size 128 kilobytes to encode the data for that first megabyte, and then it's going to spread those 10 EC cells across eight servers for the across 8 servers that are the erasure coding servers, and then 2 that are the parity servers. So you've got 10 total servers. So if you lose up to 2 servers out of those 10, you can still reconstruct your data. And so this is something that does somewhat commonly happen, where as Gordon was alluding to, a service will be excluded and go offline, and then you may not have access to your data unless you've done this erasure encoding, or at least had some sort of data integrity or parity defined. So that's all this thing is telling you. In this next slide here, I'll go into the details of how you should create your container to make this happen. So basically, as I was mentioning before, we're using a EC stripe width of 8, and with a parity of 2, that means you've got an extra 30. Well, it's an extra 20% of data, but it actually has the impact of about 33% of the bandwidth degradation over having no replication at all. And then on top of the erasure coding, we also recommend using a checksum, and the algorithm that's been proved adequate with the best performance is CRC32. And there's environment variables you can set. So the way that checksum currently works in the current version of DAOS is if there's a corruption on the right, you'll get an error, and it'll stop. If there's corruption on the read, it will retry until success. And there's an environment variable you can set to get those error messages in your job output log. And so basically, when you create your containers, so the default chunk size for a container is 1 megabyte, and that 1 megabyte is simply the greatest the amount of data that one client will write to one target at one time. And that 1 megabyte has been chosen as just sort of the default best in general performance. And so in addition to that, then there are other parameters you can set when you create the container that will enforce this having a parity level of 2 with the optimum amount of replication. So basically, it's the container create command, type is POSIX. There's a Duro class of this is RP3G1. Basically says make 2 exact full copies of the directory structure, and then the file class of EC8P2GX is basically saying use your coding with the stripe width of A with a parity of 2, which is what I showed in the previous slide, and then the EC cell size of 128K. So that the stripe width times the cell size equals the chunk size is how you get the best performance. And then eventually we'll have, there's a MKCont wrapper that does all this for you, but it's not currently updated to the latest of how we want people to run. So once that is done, then you won't have to actually specify all this yourself. You can just use the wrapper. And eventually, it doesn't work on our current version of DAOS, but you'll be able to run at EC16 P2GS, which means you'll have a much less overhead from the erasure coding. So just a couple things about how to best utilize DAOS versus Lustre or GPFS spectrum scale. So one thing about DAOS is the metadata is stored in persistent memory, as Kaushik and Gordon have alluded to. On the same server as data with low latency. So DAOS handles smaller, discontiguous, unaligned reads and writes much better than a traditional parallel file system. There really is no concept of alignment in terms of the objects that are getting stored. So there's no concept of file blocks like in spectrum scale where you just want to have one writer for one block at a time, or stripes in Lustre, where basically you want to have the file writers go across the same stripes rather. So in traditional parallel file systems, if you're using a PIO, which a lot of IO libraries do and applications do, there's collective buffering that's done to have a small number of the processes gather up and write out the data in a fashion that's optimized for the underlying file system. And this is usually just aligns data in a certain way. And because of the nature of and this aggregation phase within MPIO for this collective buffering can be very expensive. And so with DAOS, a lot of times you don't need to do that anymore. There is a point at which you still need to do that if your data is discontiguous enough and with small enough writes. But in many cases, the first thing you should do is just turn off the collective buffering if you're using MPIO and see what the performance is, and then you can turn it back on. And basically I just listed in here how you do that. Basically with MPIO, you set this Romeo hint environment variable to some hints file name, and then within the hints file, you just put in these two different parameters to disable the reading and writing of collective buffers. And then I forgot, there's some hints in here you can add for optimum data movement if you do collective buffering, and I'll put these in there for reference for the file. And then file per process is handled much better than a traditional file system. Especially with the latest Pilfer DFS or intercept library, the metadata overhead is much better than traditional file systems. And that's what this last point is trying to make, basically. You're staying in user space as opposed to kernel space. And then if you do end up doing but the buffering and it proved to be as close to or faster than not doing it. There's an alternate algorithm within within Romeo or MPI-IO on MPitch that will has it's basically a different algorithm that uses one-sided communication, and it can have much better performance in some cases. And so there's just some information here on the environment variables to set, and where you can go to read about it, and then how to use it. And if you need help with this, just let me know. And then this is just some data on checkpointing, comparing Lustre with the Flare Lustre system on Aurora versus just 24 nodes of DAOS. Basically, and DAOS has much better bandwidth, which with much better times than Flare did. Even with lamps, there was actually some extra metadata overhead in there that even despite that, DAOS was still significantly faster. So and that's it.
Thanks, Paul. I see a couple of questions that has been already answered, but I see another one. In a
Okay.
spectrum scale, there is a concept of the file set. Does DAOS have a similar concept?
A file set.
Yeah.
That'd be a question for Gordon. I'm not sure
Yeah,
there really is.
Not really. I mean, in GPFS, they had two forms of file set. They had a dependent and independent file set that either had a unique inode table just to that file set, or it shared the general inode table with the main file system. The key takeaway is that a POSIX container created within a DAOS pool, it has its own, there is no inode map per se on a container, but it emulates that it's got its own metadata. Does that make sense? I mean, usually you're going for some sort of isolation in the file set. Was that the basis of the question, Alex?
Kind of, but in GPFS, the file sets, as it was specific file system, they share the inode space.
The dependent file sets share the inode space. Correct. Yeah.
Right. But in case of containers, looks like we are talking about just individual file systems. And each file system, each container has a unique set of inodes. And yes, they're kind of unique within that container only.
Yeah. And to be clear, right? It's unique within that POSIX container, but there is no inode table. There is no inode structure. The location of data, the location of either where to place the data initially upon allocation, or where to go find that data later on a subsequent, read operation, that's all done by the placement algorithm. The placement algorithm is run and the next block is determined. So there's no need to go look up inodes. There's no concept of direct and indirect blocks. That makes sense? I mean, it's a little bit of a different, it's a little bit different.
Yeah, it's not one-to-one match.
Yeah, okay. Yeah, it's not a complete map. I'd be happy to follow up with you though. You can drop me a note if you have any follow-up questions on that.
Okay.
I spent a long time working for GPFS at IBM.
Hey, this is Rob, the MPIO guy, and I like Paul's talk on the, but I just want to. I would feel weird when people say don't turn on don't do collective IO. We haven't had a chance to really tune the DAOS driver very much, and once we get things shaken out on Aurora, I bet we're going to spend some time doing that. And then, as Paul mentioned, there's cases where collective IO is going to be a win, and cases where it won't be, and we'll be able to bake that heuristic into the driver. So right now, yeah, you have to do a little experimenting, but I wouldn't just blanketly turn off collective IO. Give it a shot. Let us know. I think I have a hunch on why some of the performance problems are there, having to do with the topology of Aurora and as Kaushik mentioned, the multiple network cards. And so we'll we'll have to work on this together to make things best for I/O. It's not going to be on day one be a solved problem, but they never are on these machines. There's always a learning curve on how to get the best performance out of this stuff.
Right.
Yes.
Yeah. It's just suggestions of what people could try to see how it is at this time. But yeah, definitely things will be improving. So thanks, Rob.
Yeah, I mean, with all the flexibility we have on container creation options, right? It's almost an infinite things to be explored, I guess.
I want to thank you, Gordon, Paul, and Kaushik. Are there any more questions?
Yeah, more like a suggestion. Coming from a user who's not an expert in all the underlying file systems and intricacies. That one of those last slides where you compare the way Lustre, like the normal classic parallel file system, the way things are written to disks and IO nodes and etc., compared to DAOS, that was very useful. And this should be right at the beginning of these presentations, in my view. That would have helped me understand more, because right from the start, you assume that everybody knows what object storage is, and I'm not that familiar with it. So
Thank you for the comment. Thank you for the comment.
Yeah, and I want to mention that I know this is a very kind of a new topic, and we are planning to have a more deeper dive probably early next year about this in a longer probably time, and hopefully with the access to a DAOS so we can actually do some hands-on. But that was a very good comment. Thank you.
But it's just that if I look at that as a user, I have to do a lot more to write to disk now, right? I have to launch, I have to get the pool, I have to use all these different commands. So I'm wondering, it's like, why do I have to do all of that just to write my data to disk, right? Well, so you kind of have to give me a carrot here saying, well, if you do that, you get like much better speed and various other goodies.
So
yeah.
if you do that, it'll go much faster.
Well, yeah, I mean,
But yeah, I get your point, Stefan. I mean, it's not the POSIX world where we sat down and taught in front of a Lustre file system. All the erasure coding decisions were already made by someone else. You know, any of the PFL layouts were already made by someone else, and you're just kind of inheriting all that work. And on this side, there's a lot of observations to be made yet, optimizations to be made yet.
right. Yeah,
But your point's well taken, and thank you for the comment.
looking forward to the next presentations.
Thank you.